Welcome to ECE 302. This is lecture 4.8 on function of random variables. I'm Professor Stanley Chan. So today we are going to learn a very useful technique, which is the transformation of random variables. If you look at our schedule so far, we have gone through many different topics in continuous random variables. Transformation of random variables is a technique that applies to all kinds of continuous random variables and also discrete random variables. The problem can be simplified as follows. You have a random variable x, and then there is a transformation g. You apply the transformation to get a new random variable, we call it y. And then we want to ask what is the PDF or the PMF or the CDF of the new random variable y. This problem arises in many different kinds of engineering problems, so we want to know how to do this calculation. The way to learn about this topic is to go through the examples. This is at least the way I learned this topic. So I'm going to show you a general principle with one slide, and then I'm going to walk you through many examples. And then towards the end of today's lecture, we're going to summarize the technique again. So let me describe the problem and then give you a couple examples, and then we'll go and we will talk about the general principle. The problem is as follows. You have a random variable x, and we assume that you know the PDF and also the CDF. Now, of course, if you know the PDF, you integrate, you will be able to get a CDF, or vice versa. If you're given a CDF, take the derivative, you will be able to get a PDF. So by knowing x, I really mean that you have access to either the PDF or the CDF or both. Now, the interesting thing comes here where we assume that you are given a transformation g. Okay, so here you have a function g. This g can be any kinds of function. Now, of course, for the sake of simplicity, we're going to assume that g is differentiable and that it is continuous and all sorts of nice things about g. But in general, this principle will apply to any kinds of g. Now you can think about what does this transformation mean. Let's say I have a random variable x, and then I want to take a square and I define it as a new random variable y. Then your g will be defined as the square operation. Or you can say that my y is going to be a cosine of x. Then your g will be a cosine function. So g can really be any kinds of transformation. Now you may wonder, why do I need to encounter this problem? Does it actually show up in engineering problems? It does. It actually shows up everywhere. For example, here in this example, you have voltage. You take the square, you times the resistor, you get the power. In this example, where you have a phase, let's say you have a theta, and then you take a cosine, then you will get a modulation of your phase. So all these problems, they show up very often in engineering problems. In data science problems, you will also encounter many different kinds of transformations. For example, y equals to 2x plus 1. What is it? Well, in this case, g will be equal to 2 times something plus 1. This is just a linear transformation of some random variables. That could happen in a data science problem easily. So knowing that, we have this transformation, and in many cases, we are not just interested in knowing the PDF, CDF of x. We want to find the PDF or CDF of y. That's the problem of this transformation random variable. And so your task is to find, as I said, the PDF and also the CDF of the new variable y. All right, so the best way to learn about this topic is to go through examples. There's no better way than going through examples because by going through examples, you'll be able to summarize a general principle, and then we're going to talk about that principle later. Let me show you a couple examples. There are 4 examples that we're going to discuss in today's lecture. The first one is a very simple example. It's a transformation. It's a linear transformation of random variable where y equals to 2x plus 3. It's a very simple problem. Okay. The second transformation we're going to learn is x squared. that is a quadratic equation. The tricky thing here is that if x is not only positive, then we're taking the square, you can actually turn some negative into positive. So we need to take care of both sides of this random variable. This is a nonlinear transformation, y equals to cosine x, which is a phase modulation problem. That will also be a very difficult problem, but we want to learn about a technique how to solve this problem. Finally, I want to demonstrate a super complicated transformation where y equals to e to the power x, and then the random variable x has this complicated PDF, where that's very different from the other cases where normally we just assume that the random variable is uniform or Gaussian or something like that. This is a very complicated PDF of x. So after the transformation of y, how are you going to get the PDF of y? So we will learn the technique over there. Okay, so let me start by describing a picture, and then we'll go into the details of each example. The problem of transformation of random variable can be summarized by this figure. What this figure says is this: you have a random variable x, and then that you have a PDF, and by integrating the PDF, you will get a CDF. So this is the CDF of your x. So CDF of x. So that is the starting point, and this is something that you are given. Now the CDF of x, I'm just assuming that the CDF of x takes this particular form, which is a uniform random variable. It's not necessarily the case, but I'm just giving you a particular example where x is indeed a uniform distribution. So that's given to you. And then now you can draw the random variables. You can draw the samples. These are the samples that can be drawn from this distribution. And because this distribution is uniform, you should expect them, the spacing between these samples, they are uniformly random. Okay, they're not necessarily equally spaced for every sample because that's still a random variable, but the distribution has to be uniform because your CDF is uniform. Okay, so these are the dots that you would normally generate. That's your x. Okay, then we go to here. We go to this black line. That is the transformation. That's y equals to gx. That's a transformation. Okay. In this case, I'm just creating some arbitrary function here. So that's a gx. And then after the gx, what will happen to the samples? Let's look at a particular sample in this diagram. For example, here, let's look at this sample. After the transformation, where will the sample go? Well, the sample will go to here and then go to here. Do you see that? If you are looking at this sample, it will go up here and it will go there. Okay, so now you trace all these samples. You go to the y-axis. There is something very interesting happening, that these two samples, they got squeezed together on the y-axis. That's because of the transformation that's happening. Okay, now if you have uniform spacing between these two samples and then you go up, because of the curve here, that will map these two samples, they will squeeze them together. Versus if you have these two samples, you go up to here, they will stretch, they will go out by the curvature of this transformation. All right, now given this set of samples, so these are the new transformation, right? So these are the distributions of y. These are the y's. All right, so these are the y's. These are the x. So now you ask, what is the CDF of y? Well, then you need to do this cumulative sum of all these samples. So now you have more samples here, so it will go up faster in the beginning, and then you have more spacing there, and so you go up slower towards the end. And so that will be the shape of the CDF of the transformed variable y. Okay, and then you take the derivative. Then you are going to get this derivative, which is the slope of your curve. In this case, it's more like Gaussian, but that's a cartoon illustration. Right? So now you can see that there is a process going on in this diagram. If I start with x, I need to look at my transformation G, and then I need to look at the samples, and then I need to calculate the CDF, and then towards the end, I'll be able to find the PDF. So this diagram also tells you that we will never jump from the PDF to the PDF. The process to go from the PDF to PDF will be go to the CDF, transform, go to the new CDF, take derivative, go to the PDF. That is the general principle. Now, of course, by describing the general principle, you won't be able to do any actual calculation. So what I'm going to do is to walk you through 4 examples as I promised in the beginning. Okay, let us work on example number 1. This example is a very simple example. It says that I have a random variable x. It has a PDF fx, and then it also has a CDF capital Fx. The transformation I'm assuming is y equals to 2x plus 3. It's a linear transformation. It's a very, very simple problem. I want to find the PDF and CDF of the transformed variable y. Okay, let us go back to this diagram again. Okay, let us try to think about how we should do it. This diagram says that I will start with some kind of distribution, which you may well just assume that it is uniform, but it doesn't need to be uniform. Anyway, there is a transformation which says that a g of x equals to 2x plus, is it 3? Okay, so that's 3. So you can draw a curve, which would be a curve like this. All right, and then after this transformation, what will happen? Well, you have these samples go up, these samples go up. Here you don't have any samples, right? So you will have these samples go up. Now, because this is a straight line, what we should expect is that these samples, they will be also following the same distribution, although the spacing would be a little bit different, but it will still be linear. Okay, and therefore what we should expect to see, it will be that it will be a simple translation scaling of the original PDF or CDF. Now let us work out some details of the equations to make sure that you understand how to do it. The CDF of y, okay, which is defined as this, it is really the probability that y is less than or equals to small y. So that's the definition of a CDF of y. And then what is it? Well, this is the probability that your 2x plus 3 is less than y, right? What I'm doing is that I'm just replacing the y by 2x plus 3. And then what do I have? Well, then you have probability of x less than y minus 3 divided by 2. What am I doing? I am just rearranging the terms by moving the 3 to the right-hand side, divide 2 by both sides. I will get to this quantity. Now, the magical thing happens here. This is a probability applied to a random variable x, evaluated at the upper bound of some quantity. Okay, it's just some quantity. It doesn't matter what quantity it is. It's some quantity. It is a random variable of y. Okay, and now you recognize what is the form of this: x less than something. Okay, this something this just the CDF of x evaluated by this something. Okay, that is exactly the CDF of x evaluated by something. That's why we have this CDF of fx of y minus 3 divided by 2. So what we have shown is that we start with fy and we have found if a function written in the form of fx. And then we can find the fy. What is small fy? That's the PDF. The PDF is the derivative, okay, of fy of y. Now what is fy? Well, the fy is just fx of y minus 3 divided by 2. Okay, that's just the substitution of what we have found in the previous step. And then when you take the derivative of this thing, this is a function of y. So if you take the derivative, you will get fx prime of y minus 3 divided by 2, and then you have d of dy of y minus 3 divided by 2. That's a chain rule. The chain rule says that I'm going to take the derivative of the outer function, and then I'm going to take the derivative of the inner function. The outer function is what? The outer function is just fx prime, but fx prime, if you recall, what is it? This is just fx at y minus 3 divided by 2. Why? Well, this is because that the derivative of a CDF is exactly the PDF. And then what is this term? This term is the derivative of this y minus 3 divided by 2. Take the derivative with respect to y. So you have 1/2 over here. The 3 will be gone. And that's why you have this result, that the PDF of y is written in terms of the PDF of x in this form. Okay, now you can plug in your favorite distributions. For example, you may say that my x is uniform in 0 and 1. Then my fx will just be 1 when x is between 0 and 1, and then otherwise you plug this number in, then you will be able to calculate the PDF of your y. Okay, and then if you integrate, you will be able to get the CDF of y. So this example illustrates the basic principles of our problem. You start with a PDF of x or CDF of x. You first find the CDF of y, and then you take the derivative. You will be able to find the PDF of y. So this is example number 1. It's a very easy example. Perhaps we can move on to the second example. The second example says that you have a random variable x, and then you have this transformation y equals to x squared, and then you want to find fy and fy. So according to the principle that we have just learned, the idea is to first find the CDF of y, and then we are going to take the derivative to find the PDF of y. So let's see if the same principle will work. The CDF of y is the probability that y is less than small y. Okay, and then now we can substitute the y by x squared, so that you have probability of x squared less than or equals to y. And then what? Well, this is the tricky part. If you have x squared less than y, you are not just getting x less than square root of y. You're not just getting that. You also get minus square root of y, because you have two sides of this square root. So when you have this, you recognize this as what? Well, this is the probability that x is lying between the two numbers. This can be evaluated as the CDF evaluated at the square root of y minus the CDF evaluated by the lower end, which is minus square root of y. And so you can see that the CDF of y is actually given by the CDF of x with a difference on two ends of the CDF of x. So that's a little bit different from the previous example where you have the two ends. Now, let's also calculate the PDF of this random variable y. The PDF, as we have seen, it will be the derivative with respect to your y of your fy of y. Now, what is this derivative? It will be d dy. You have this fx of square root of y minus fx of minus square root of y. Okay, and then now if you take the derivative by chain rule again, you will have fx prime of square root of y, and then you have d square root of y and dy minus f prime of y Now, because you have this minus sign here, you will get to this plus sign, and then you have dy of square root of y. Okay. Of course, if you like to be a little bit more precise, you can have minus here, and then you can put a minus there. Now, let us do some calculation. This is the square root of, this is the PDF, CDF of y taking the derivative. So this is exactly the PDF of y, so that's the square root. Now, if you take the derivative of this guy, you have 1/2 of square root in the denominator. This thing would be fx at minus y, and then you have a minus sign, so that would become a plus, and then you have 1/2 y. Okay, so you can see that after doing all these calculations, you have a solution in this form. Now again, if you prefer to put in a particular distribution, for example, the uniform distribution, you're welcome to do so. Just plug in into this equation, and you'll be able to find the expression of your PDF as well as this CDF. So this example number 2 illustrates something addition to the previous example number 1, where we need to take care of both ranges. You have a lower tail and then you have the upper tail. We need to take care of both. This slide is a follow-up question, which says that if you indeed assume that x is a uniform random variable in a range of a and b, and then you let y equals to x squared, then the CDF and the PDF you can find in this way. Okay, and then the range of y would be living in between a squared and b squared, because if x is between a and b, then of course y is between a squared and b squared. The expression of your fy is found according to the previous formula here. Now I will leave this as an exercise. I hope that you can try to make sure that you understand how to calculate this. The idea is that you first write down the PDF and CDF of your x, follow this derivation and plug in the equation and numbers, and see if you get the same results as I am getting here. This is a diagram showing you what is happening in the calculation. We start with a uniform distribution, and then we're going to send these samples up. And then you can see that there are lots of compression going on in the lower tail, and then there is a lot of stretching in the upper tail. And therefore, this would be the CDF of your new variable y. And after you take the derivative, you will be able to get to this form. Now, note that this is exact in the sense that this square root function is indeed a curve that looks like this. So there is really no cheating here. This expression is the expression that we can derive from the previous 2 slides. And this is a function of square root y. It takes this form exactly. And then the PDF, as what we have derived, is 1 over square root of y. And then if you take the derivative of this fy, you will indeed get this expression, and it's going down. So that would be the PDF of your new variable y. So we have gone through 2 examples. I hope you are still following us. I am going to show you one slightly more difficult examples, which is example number 3. And then I'm going to show you an apparently more difficult problem, which is example number 4, but that is a trick to solve that problem. Okay, so let us work on this example number 3. Let's apply the same principle again and see if we can get the answer. So this example says that my x is uniform between 0 to 2 pi, and I'm defining cosine x as my y. So let's find the PDF and CDF of y. In this problem, since I have already given you the PDF of x, I've already given you the distribution of x, we will be able to find the CDF and also the PDF. The PDF should be straightforward. You have fx of x, that is 1 over 2 pi or 0 if your x is between 0 and 2 pi or 0 otherwise. Okay. Now, how about the CDF? The CDF will just be integration from 0 to x, and then you have 1 over 2 pi dt. T is a dummy variable, and then this is your PDF. So if you integrate, you will get this t over 2 pi. You evaluate at x and then 0, so that will give you this x divided by 2 pi. So that is your CDF of x. That is for this guy. Now we are interested in finding the CDF of y and PDF of y. How do we find that? Well, let's find the CDF of y first. The CDF of y, of course, is the probability that y is less than small y, and this is the probability that your cosine of x is less than y. Okay, so now there is a little thing here we need to worry about, because if you have a cosine function, well, of course, you can take a r cosine on y, right? So that is of course true, but this cosine function is also a little bit tricky in the sense that you have this thing going on. Okay, so now you say that cosine of x. So this is cosine of x. Cosine of x is less than y. So y would be a line here. So that's your y. And then you say that cosine x, which is this curve, is lower than the straight line. So now you're looking at this range of values, right? And so it will be from here to here. So what is it? Well, here it would be a y. Okay. No, so this is cosine inverse of y. The other value here, this is actually 2 pi minus cosine inverse of y. Okay, because there's a period here. So now you have this 2 pi minus cosine inverse of y. So you have one end and the other end according to this curve. Once you have this, then you know that the CDF can be easily written down, which would be the CDF of 2 pi minus cosine inverse y minus cosine inverse y. And then what? Since you already have the CDF of this x, right? So which is here, you just plug it in. That will give you what? So that will give you 2 pi minus cosine inverse of y divided by 2 pi. So that is the first one. And then the other one will be cosine inverse of y divided by 2 pi. And then you can do the cancellation, and then there will be half and half, but they have both minus, so you can add them up. So that will give you 1 minus cosine inverse of y divided by pi. So this is the CDF of your new variable y. Now, how do we calculate the PDF of y? The PDF of y is, of course, the derivative of your CDF. Now, you need to take the derivative of this guy. This guy involves 1 minus cosine inverse of y. Now, I give you a hint here that dy of cosine inverse y is minus 1 over the square root of 1 minus y squared. So if you trust me, you plug this equation into this derivative here, you'll be able to get the solution. So the fy of y is given by this. Now, of course, some of you may wonder, all right, how do you ever come to this magical formula that the derivative of cosine inverse of y is given by this formula? Now, this is a calculus problem. It's a very easy calculus problem, which I can explain. Let's say you have a triangle, okay? This is a triangle, and then you define this thing as theta, and then you have the horizontal line is y, and then the diagonal line is 1, okay? And by the right triangle and the Pythagorean principle, we know that this is a square root of 1 minus y squared. So we can calculate everything. Now, what is this theta? Well, we know that cosine theta equals to y divided by 1, right? It would be this line divided by this diagonal line. So that's y. And then suppose we take dy on both sides of this equation, okay? And then you have cosine theta here. Then what do you have? Well, you have first of all, you have sine theta, and then d theta dy, and then here you have 1. Now, this d theta of dy is what? Well, we know that cosine theta is y, and so theta has to be cosine inverse of y. And so now you have a d theta cosine inverse of y sitting here. And so the only thing you need to calculate would be this 1 over minus 1 over sine theta. By the way, what is sine theta? Sine theta is actually quite easy from the diagram. Sine theta would be this divided by that. Okay, so that would be minus 1, and then you have 1 minus y squared divided by 1. If you do the calculation, then you have 1 over 1 minus y squared with a minus. Right, so now you go back to here. Wait, this is y. Okay, so go back to this equation here. You say, wait, what is the derivative cosine inverse? Well, the cosine inverse is exactly this expression, which is there right here. So now you can plug it in. You will get the answer. So this only involves some little trick in the calculus. But other than that, I hope you can see that the calculation itself is pretty straightforward. You find the CDF and you find the PDF. And the only thing that you need to worry would be figuring out the range. And that's pretty doable if you draw a diagram. Okay, so that is example number 3. I hope you are still with us. And then let me move on to the last example, and then we can summarize what we have learned so far. So the last example is this. You have a PDF of a random variable, which is extremely complicated formula. And then you have a transformation y equals to e to the power x, and we want to find the PDF. Now, the principle says that you have to first calculate the CDF of y, which is this, which is also, according to our definition of the problem, it will be probability of ex less than y. Now, this e to the power x is an increasing function. So an increasing function means that you have x, it will be less than log of y. So that will work. Okay, and then what? Well, this is just the CDF of x evaluated at log y. So that would just be fx evaluated at log y. Now, what is fx? Well, I don't have the formula for fx, and I don't want to integrate this PDF to get a CDF, but that's fine because this is just the integration of my PDF of x. Okay, integrating from minus infinity up to the point of log y. Right, it is this log y here. This t is just a dummy variable, so that's pretty easy for me. So now let's see, what do I have? Well, you have this thing, and you just replace your fx of t by your fx, dummy here. You can get this expression. That is your CDF of y. Now, of course, I have not computed this integral, and I have not give you a closed form expression of my fy. But that's fine, because the problem is not asking you to find the CDF of y. The question is asking you to find the PDF of y. So how do we find the PDF of y? Well, the PDF of y is the derivative dy of your fy of y. And then that is the dd at y of the integration from minus infinity to log y of some magical things, which is a EX, EX, and then E minus A, EX, and then there's a DX over here. This is super complicated, but never mind. You're taking the derivative outside. So what we can do is that we can match the terms so that we have a D of dy, and then we can have a D of D log y. So I have a log y over here, and then I have the integration, this minus infinity to log y, and then EX, E minus A, EX, dx. This is still very complicated, but now I hope you guys see the pattern. There is a term here which is matching with the upper limit, and therefore by the fundamental theorem of calculus, this is equal to A times E to the power log y. I'm just replacing x with this log y, and then you have E minus A, E to the power log y. This is the integral here. And then we can do some simplification. That will give you a what? E to the power log y. So that is y. Okay. And then e to the power log y. So that's e minus a y. Okay. So that is your expression. And then how about this term? That's just 1 over y. Okay. And so now you can do a cancellation. This term will cancel with that term, and so you will have left with a e minus a y, which is exactly the answer I'm giving you in this problem. Okay, so the trick of this example is that you do not need to calculate the CDF if your end goal is to find the PDF, because the fundamental theorem calculus will help you bypass the complication of finding the expression for the CDF. Alright, so to summarize, we have learned a very useful technique, which is called the transformation of random variables. The idea really just involves 2 steps. One is to find the CDF, the other one is to find the PDF. And that is the general principle for this type of problems. There are some rules of thumbs. The rules of thumbs will involve 3 points. One is that always try to find a CDF, and then you ask yourself, what are the eggs such that this will happen? And I am especially mention this cosine example because you need to understand that, let's say here is your function, and you want to figure out what kind of x will be below this cutoff line y. So you need to find out this range of x. So determining the range of x that will satisfy your criteria, that is a very important step. The second important rule of thumb is that sometimes you do not need to explicitly solve for the CDF. This is example number 4. Okay, you can use the fundamental theorem of calculus to bypass that calculation and just directly go to the PDF. The third rule of thumb for this type of problems is to draw pictures. You can see that I have given you a picture in the beginning. That picture is very illustrative. I hope that you can spend some time, try to understand how we come up with this picture. And if you can draw this picture by yourself, you will be able to solve this problem a lot easier. So this is the end of today's lecture. I hope you have found this interesting. There will be problems, promise, for the homework problems and also the exam problems with very high likelihood. We're going to ask you some questions on this problem. So I hope you can practice and make sure that you know how to solve this type of problems. If you ever have any question, please post your question on Piazza or send an email to any of the instructors. We'll be very happy to help you. Okay, thank you very much for watching this video. I hope to see you again next time.